You know that feeling, right?
Yeah.
You're trying to learn machine learning, and it just feels like you're drowning in information.
Oh, absolutely. Endless code, so many algorithms. It's overwhelming, like drinking from a fire hose sometimes.
Exactly. But what if there was something more elegant, kind of beacon? For us, that's really Scikit-learn.
Yeah, it brings a certain order to the chaos.
So in this deep dive, we're not just going to list commands. Nope. We want to give you a shortcut to really getting Scikit-learn.
Right. Going beyond just the surface level.
We'll peel back the layers, look at its core ideas, the philosophy behind it, some advanced stuff, and crucially, how it fits into actual MLs, the professional side.
Think of it like getting the master key, the key to building ML systems that are solid, robust, and actually deployable. That last part is key.
Totally. So our mission today.
Simple, really. We've gone through the sources, pulled out the most important bits, the real nuggets of knowledge.
To give you clarity.
And confidence, so you can use Scikit-learn like an expert, making smart choices.
Okay, let's unlock that first part then. The Zen of Scikit-learn, or what some sources call its elegant software engineering contract. Sounds a bit formal, maybe?
It does, but it's actually a really powerful idea. It's all about consistency, composability, making things fit together easily.
And extensibility, right? Making it easy to add your own stuff.
Exactly. And at the very heart of it all is the estimator.
Okay.
It's basically any object that can learn from data, and every single estimator has a fit method, always.
That consistency sounds huge. Means you learn it once.
And you can apply it everywhere, whether it's linear regression or a random forest or, something totally custom you build later. Fit works the same way conceptually.
Huh. It hides the complex math differences.
Right, so you can swap algorithms in and out with hardly any code changes. Great for trying things out, A/B testing models.
Yeah, that definitely lowers the mental load. So the estimator's the core. And you mentioned a smart separation in its design between setup and training.
Absolutely critical.
Sure.
Scikit-learn draws a really hard line between the init method.
That's where you set your hyperparameters, like the knobs you tune before training.
Precisely. That's init. Then there's the fit method. That's totally separate. That's where the learning from data actually happens.
Okay. And what about after it learns? How do you know what it learned?
Good question. Conventionally, those learn parameters, like, say, the coefficients in a linear model or the mean it learned for scaling, they get stored as attributes with a trailing underscore.
Oh, like coef or mean. I've seen those.
Exactly. So you can instantly see what the model learned from the data versus the hyperparameters you set beforehand. Super helpful for inspection.
That does make it way clearer. Okay, so beyond the basic estimator, the sources talk about three main interfaces: estimator, predictor, and transformer. Can you break those down?
Sure. Estimator's the base, right? Provides fit XY to learn. Think logistic regression or even standard scalar.
Okay.
And predictor builds on that. It adds a predictx method for actual predictions, classifications, regressions.
Like random forest classifier.
Perfect example. And often predict probe X too for probabilities.
Got it. And transformer.
Transformers are special estimators for data conversion. They learn something in fit, but then they add a transform X method to actually change the data based on what they learned.
Like the standard scalar example. It learns the mean and standard deviation in fit.
And then uses transform to scale new data using those learned values.
Right. And this is where it gets really powerful for building systems, because one object can be multiple things.
Exactly. That interchangeability is core. Like K means clustering. It's an estimator, sure, but it's also a predictor because it can assign new points to clusters.
Or standard scalar is both an estimator and a transformer.
Precisely. And this ties into another Scikit-learn idea, duck typing.
Duck typing. If it walks like a duck.
And quacks like a duck, it's a duck. Scikit-learn cares more about behavior than strict inheritance. If your custom object has a fit method and looks like an estimator, Scikit-learn will usually just accept it.
Wow, okay. So you don't always have to inherit from their base classes.
Yeah. Not necessarily, especially for simpler cases. It makes integrating your own custom code much, much easier.
So let's pull this together. The design, the consistency, the separation, these interfaces.
Yeah.
Duck typing, what's the big win for practitioners?
It just makes life easier. Less thinking about boilerplate, more thinking about the problem. You can try different models quickly, build complex workflows step by step. It's not just a random collection of functions, it's a system.
A system designed for building bigger systems.
You got it. And that structure, that composability, directly leads us to tools like Pipeline and ColumnTransformer. They really leverage this elegant contract to handle real-world messiness.
Okay, let's talk about that messiness.
Yeah.
Because real production ML, rarely just fit predict on a nice clean CSV, is it?
Oh, definitely not. You've got raw data, maybe multiple pre-processing steps, categorical features, numerical ones, and then the really scary stuff.
Like data leakage.
Exactly. Like maybe you accidentally fit your standard scalar on the whole data set before splitting train and test.
Ouch. Your validation scores look amazing.
But they're totally wrong because your scalar saw the test data during training. That's leakage.
And then there's training serving skew, making sure you do the exact same thing in production as you did when you trained.
That's another huge one. Subtle differences in pre-processing between your notebook and your deployment can kill performance. These are common, painful problems.
And pipeline is the fix for the sequential stuff, right?
Yeah.
Bringing order.
Pipeline is fantastic. It chains together steps, usually transformers, then a final estimator into one single object.
One object that acts like an estimator itself.
Yep. And here's the magic. When you call fit on the whole pipeline, it automatically calls fit transform on each transformer in sequence, passing the output of one to the input of the next. And only then does it call fit on the final estimator using the fully transformed data.
Yeah. So when you use it with cross-validation,
It automatically prevents that data leakage. Each transformer only learns from the training fold it's supposed to see. It's declarative. You define the steps, pipeline handles the correct execution.
that's really neat. But what if your data isn't just one sequence? Like you need to scale numerical columns, but one hot encode categorical ones.
Right, heterogeneous data, that's where ColumnTransformer comes in. It's designed specifically for that.
How does it work?
You basically tell it which transformers to apply to which columns. You define it using tuples, like name, transformer, list of columns.
So you could say, apply standard scalar to these numerical columns and one hot encoder to these categorical ones.
Exactly. And it handles applying them in parallel and bringing the results back together correctly. Super flexible for complex data prep.
And then you can put a column transformer inside a pipeline.
Now you're thinking, yes, you combine them. Often the first step in your pipeline is a column transformer to handle all the different feature types. Then maybe some other steps, and finally your model.
Wow. So that combination, pipeline plus column transformer, that encapsulates the entire thing. From raw input to final prediction, all in one object.
Precisely. And that single object can be saved, versioned, deployed, which leads to that great quote.
One does not deploy a model. One deploys a pipeline.
Bingo! Because the pipeline is the model, plus all the pre-processing needed to make it work, it guarantees reproducibility, simplifies deployment massively, and enforces that scientific rigor. Saves you from so many headaches down the line.
Okay, that's incredibly powerful for production. Pipelines and column transformers handle a lot. But what if the built-in tools aren't quite enough? You need something really specific for your problem, some unique feature engineering.
Yeah, that happens all the time. You often have domain knowledge, specific business rules, or just weird data quirks that require custom logic.
Things Scikit-learn couldn't possibly anticipate.
Exactly. You need to build your own transformer.
And for the simple cases, the quick fixes, there's function transformer, right?
Yep. Function transformer is pretty handy. You can wrap basically any Python function in it.
Like taking a log or squaring a feature.
Perfect examples. Stuff that doesn't need to learn anything from the data. It just applies a fixed rule. That's why we call it stateless.
Ah, stateless. Okay. But what if your transformation does need to learn? Like, say, imputing missing values, using the mean calculated only from the training data.
Right. That's a stateful transformation. The mean is the state learned during fit.
Right.
Function transformer can't do that.
Because it doesn't have a fit method to learn that state.
Exactly. For anything stateful, learning an imputation value, learning categories for encoding, learning scaling parameters, you absolutely must create a custom class.
Okay, so writing your own class, that sounds a bit more involved. Are there rules for making it play nice with Scikit-learn, like fitting into pipelines and grid search?
There are, and they're important for seamless integration. First, you should inherit from sclearn.base estimator.
Try that one.
That gives you methods like getParams and setParams for free, which things like grid search CV need to tune your hyperparameters.
Oh, makes sense. What else?
You should also inherit from sclearn.base transformer mixin. That magically gives you the fit transform method, which is super convenient. It just runs fit, then transform.
Okay, base estimator and transformer mixin, got it.
Then, inside your class, you need an init method to accept and store any hyperparameters you want to define for your transformer.
Like maybe the threshold value or a strategy setting.
Exactly. Then, the core methods, fit self x, y, none. This is where you learn from the data x and maybe y, though often not needed for transformers. You calculate your state, like the mean or the categories, and store it as an attribute with a trailing underscore.
That underscore convention again.
Yep. And crucially, fit must return self.
Return self. Okay. Why?
It's how Scikit-learn allows method chaining and fits into the pipeline structure. Just remember, fit, return, self.
Got it. And finally.
Finally, transform self, x. This takes new data x, uses the state you learn and stored in fit, stuff with the underscore, applies your transformation logic, and returns the transformed data.
Wow. Okay, so it's a bit of boilerplate, but it follows that consistent estimator transformer pattern.
It does. And here's the payoff, the real aha moment. Once you've built your custom transformer like this, it slots perfectly into Pipeline and ColumnTransformer. You can tune its hyperparameters using grid search CV right alongside your model's hyperparameters.
Seriously. So my custom domain-specific feature engineering step becomes just another tunable part of the whole automated workflow.
Absolutely. Encapsulated, reusable, optimizable. That's a massive leap for doing professional, maintainable ML work. It lets you turn your specific insights into robust parts of the system.
That really is a game changer. Okay, so we know how to build these workflows. Let's zoom in on the algorithms themselves. Understanding what's going on inside them, the levers we can pull, that seems key to moving beyond just being a user.
Definitely. Knowing the algorithms helps you choose the right one and tune it intelligently, not just blindly grid searching everything.
Let's start with a really popular one, gradient boosting machines, GBMs. They sound complex.
They can seem that way, but the core idea is actually quite intuitive. Think of them as building a team of predictors, usually simple decision trees one by one. Yes, sequentially. And here's the clever part. Each new tree doesn't just try to predict the target. It tries to predict and correct the errors made by the team built so far.
Ah, so it focuses on what the previous trees got wrong, like boosting the performance by fixing mistakes.
Exactly. It's fitting the pseudo-residuals, which are basically the errors of the current ensemble. It's often described as gradient descent, but in the space of functions rather than parameters. Each new tree moves the overall prediction closer to the true target.
That's a cool way to think about it.
Yeah.
Okay, tuning GBMs. What are the critical hyperparameters we need to know?
Number one is probably estimators how many trees are in the sequence.
More trees, always better.
And not necessarily. That leads to overfitting, which brings us to learning great. This controls how much each new tree contributes to the final prediction.
So they're related.
Highly related. A smaller learning rate means each tree has less impact, so you generally need more estimators, more trees to reach good performance, but it often leads to better generalization. It's a trade-off.
Okay, estimators and learning grade. What else?
Max depth is crucial. It controls the complexity of each individual tree. Deeper trees can capture more complex patterns, but also overfit more easily.
Right.
And then there are parameters like subsample and max features. These introduce randomness by only using a fraction of the data or features for building each tree.
Why add randomness?
It acts as regularization. It prevents the trees from becoming too correlated and helps the model generalize better to unseen data. It's a bit like dropout in neural networks.
Gotcha. Now, tuning estimators sounds like it could take forever if you just try a bunch of values. You mentioned a smarter way.
Yes, definitely don't just grid search estimators over a huge range. It's super inefficient. The standard, much better practice is early stopping.
How does that work?
You set aside a small validation set during training. As the GBM adds more trees, you monitor the performance on this validation set. If the performance stops improving, or even starts getting worse for a certain number of rounds,
You just stop adding trees.
exactly. You stop the training automatically at the point where validation performance was best. It finds the optimal number of trees for you, prevents overfitting, and saves a ton of computation time. It's almost always the way to go.
Okay, that makes a lot of sense. Now let's switch gears completely. From sequential error correction with GBMs to a different philosophy. Support vector machines, SVMs. You called it the art of the margin.
Yeah, SVMs approach classification differently. The core idea is to find the best possible dividing line or hyperplane between classes.
Best possible. What does that mean here?
It means the hyperplane that has the largest possible margin. The margin is the distance from the hyperplane to the nearest data points of any class.
So it's trying to create the biggest possible buffer zone between the classes.
Precisely. And the data points that sit right on the edge of this margin, those are the crucial ones. They're called the support vectors.
Why support vectors?
Because they literally support or define the hyperplane. If you moved any other points around, the optimal hyperplane wouldn't change, but if you move a support vector, the line might have to shift. It's quite elegant the boundary is defined only by the most difficult points.
Okay, that works for linearly separable data. But what if the data is all mixed up, nonlinear? You can't draw a straight line.
Right, and that's where the magic of the kernel trick comes in, especially the RBF or radial basis function
The
kernel.
trick sounds fancy.
It's conceptually amazing. It allows the SVM to operate as if it's mapping the data into a much higher dimensional space.
Where maybe a linear separation is possible.
Exactly, but here's the trick. It does this without ever actually calculating the coordinates in that high-dimensional space. It uses the kernel function to compute the relationships between points as if they were in that higher space.
Whoa. So it avoids the massive computation of those extra dimensions.
Yep. It's computationally efficient, but gives the SVM the power to find really complex, nonlinear decision boundaries. Think of it like finding a curved line by cleverly using only straight line math in a hidden higher dimension.
Okay, that's clever. Now, tuning SVMs, the big parameters seem to be C and gamma. They look intimidating.
They are critical and they interact. Let's break them down. C is the regularization parameter. Think of it as the cost of misclassifying a point.
Cost.
Yeah. A low C means the SVM prioritizes a larger margin, even if it means misclassifying a few points. This leads to a simpler, smoother boundary, potentially higher bias, lower variance, more tolerant of errors.
Okay, and a high C.
A high C means the cost of misclassification is high. The SVM will try very hard to classify every point correctly, which can lead to a smaller margin and a more complex wiggly boundary that might overfit. Lower bias, higher variance.
Right, the classic bias variance trade-off.
Yeah.
Gamma, that's specific to kernels like RBF.
Yes. Gamma defines how much influence a single training example has. Think of it like the reach of a point. A low gamma means points have a far reach. Their influence is wide. This leads to a smoother, more general boundary, potentially underfitting if it's too low.
And high gamma.
High gamma means each point has very localized influence, only affecting its immediate neighbors. This can lead to a very complex, highly sensitive boundary that closely follows the training data classic overfitting.
So C and gamma together control the shape and complexity of the boundary. You really need to tune them together.
Absolutely. And one crucial thing with SVMs, they are not scale invariant. You must scale your data, like with standard scaler, before training an SVM. Otherwise, features with larger values will dominate the distance calculations, and the SVM won't work well.
Good tip. Okay, let's pivot again back to linear models, but with a twist. Regularization. Ridge, Lasso, elastic net. Why do we need these?
Standard linear regression can run into problems, especially if you have many features or if some features are highly correlated, multicollinearity. The coefficients can become very large, unstable, and overfit the training data. Regularization adds a penalty term to the loss function to prevent this.
A penalty for what?
A penalty for large coefficient values. It encourages the model to find simpler solutions.
Okay, so ridge regression, that uses an L2 penalty.
Right. The L2 penalty adds the sum of the squared coefficients to the loss. This has the effect of shrinking all coefficients towards zero.
Towards zero, but not exactly zero.
Correct. Ridge will make coefficients small, but it very rarely makes them exactly zero. It's great when you think most of your features are probably relevant, and it handles multicollinearity well by distributing the effect among correlated features.
Okay. Then there's lasso regression. L1 penalty. What's different?
The L1 penalty adds the sum of the absolute values of the coefficients. This seemingly small difference has a huge consequence. Lasso can shrink some coefficients all the way down to exactly zero.
Ah, so it performs feature selection automatically.
Exactly. If a feature's coefficient becomes zero, it's effectively removed from the model. This makes Lasso really useful for high-dimensional data where you suspect many features might be irrelevant. It gives you a sparser, potentially more interpretable model.
Interesting trade-off. Shrinking versus selecting. What if you want a bit of both?
Then you use ElasticNet. It's a hybrid. It combines both the L1 and L2 penalties. You control the mix with another hyperparameter.
Why combine them?
It gets the best of both worlds. It can perform feature selection like Lasso, but it's also better behaved than Lasso when you have groups of highly correlated features. Lasso tends to arbitrarily pick one feature from a correlated group and zero out the others, while ElasticNet is more likely to keep or discard the whole group together.
Ah, okay. So the choice depends on your data. If you have tons of features, maybe Lasso or ElasticNet. If features are correlated, maybe ridge or elastic net.
Precisely. Understanding these differences lets you choose the right tool based on what you suspect about your data rather than just guessing. It's about making informed choices.
Moving from algorithms to actually deploying them. A great model in a notebook is one thing, but production, that's a whole different ballgame. MLOps, where do we start?
First step after training is saving your model. Persistence.
Pickling it.
You can use Python's pickle, but for scikit-learn models, joblib is generally recommended.
Why joblib?
It's optimized for saving objects that contain large NumPy arrays, which is exactly what scikit-learn models are full of. It's often more efficient, especially for bigger models or pipelines.
Okay, joblib. But then there's this problem. The versioning crisis. Sounds dramatic.
It can be. Imagine you save a model using scikit-learn version 1.2. Then you try to load it in an environment running version 1.4. Sometimes it just breaks, silently, or with cryptic errors. Dependencies change.
Nightmare fuel for deployment. So how do you solve that? You can't just save the model file.
Nope. That's not enough for robust production systems. You absolutely must persist the entire environment associated with that model.
The whole environment. What does that include?
It means saving the serialized model file itself, the .joblib file, but also the exact requirements.txt file, pinning the versions of scikit-learn, NumPy, pandas, everything you use.
So you can recreate the exact software environment.
Exactly. Plus, ideally, the training script you used to create the model and some reference or identifier for the exact training data set. Maybe even hash the data.
Wow. Okay. That's much more comprehensive. It's about total reproducibility.
It is. It's the only way to be sure you can reliably load and run that model later or debug it if something goes wrong. It tackles that works on my machine problem head on.
You also mentioned scops.io and ONNX briefly.
Yeah, those are more advanced considerations. Scops.io is newer, aims to be more secure for loading models from potentially untrusted sources compared to Pickle Joblib. And ONNX is about framework interoperability, saving a model in a standard format that other tools, maybe not even Python-based, can understand. Useful for certain deployment scenarios.
Okay, so model saved with its environment info. Next step is making it usable, right? An API?
Usually, yes. You wrap your loaded model or pipeline in a web API, a simple web server. Frameworks like FastAPI or Flask are really common for this in Python.
And you typically make like a POST endpoint. Send data to it, get a prediction back.
Exactly. Send JSON data in the request body. The API loads the model, calls predict or predict proba, and returns the result, probably also as JSON.
And it's good practice to define the expected input, right? Like the schema.
Oh, absolutely. Using something like Pydantic to define the expected input data structure is crucial. It gives you automatic data validation. If someone sends data in the wrong format, the API rejects it immediately with a clear error, instead of your model crashing unpredictably later. Saves a lot of debugging.
Okay, API defined. Now, how do we package this whole thing, the API code, the model, the dependencies, to really nail that reproducibility and avoid the versioning crisis?
Containerization. Docker is the standard answer here.
Docker. So you build an image?
Yep. You write a Docker file that specifies everything, the base operating system, the Python version, copying your requirements.txt and installing dependencies, copying your API code and the model file. Docker bundles all of that into a self-contained, immutable container image.
Immutable meaning it doesn't change once built.
Exactly. That image contains everything needed to run your API, locked down to specific versions. You can then run that container anywhere. Docker runs your laptop, a testing server, the cloud, and it will execute identically every single time.
That completely solves the "it works on my machine" problem.
It's the gold standard for reproducible deployments in MLOps.
But wait, deployment isn't the end, right? Models don't just live happily ever after in production.
Definitely not. That's a critical, often underestimated part of MLOps. Models degrade. It's inevitable. We call it model decay or drift.
Drift, meaning the world changes and the model gets stale.
Pretty much. The real-world data your model sees in production will eventually start to look different from the data it was trained on. Patterns shift.
Okay, what kinds of drift are there?
We usually talk about two main types. First is data drift, sometimes called covariate shift. This is when the statistical properties of your input features change, like maybe the average income of your users goes up or the distribution of browsers they use shifts. The inputs change.
Even if the relationship between income and buying something stays the same.
Right. The inputs themselves drift. The second type is concept drift. This is more fundamental. It's when the relationship between the input features and the target variable actually changes.
Like customer preferences change,
Yeah.
so what predicted buying behavior last year doesn't work anymore.
Exactly. Or maybe a competitor changes pricing, fundamentally altering purchase decisions. The underlying concept the model learned has shifted.
So how do you deal with this inevitable drift? You can't just leave the model running forever.
You absolutely need monitoring, proactive monitoring. You need systems in place to track the statistical distributions of the input features your live model is receiving. Are they diverging significantly from the training data distributions?
Okay, track the inputs. What else?
Track the model's performance metrics, too. If you can get ground truth labels for the live predictions, even with a delay. Is accuracy dropping? Is error increasing? You need dashboards and alerts for this.
And when you detect significant drift.
That's the trigger. It means the model is likely no longer optimal, maybe even harmful. It signals that you need to investigate, retrain the model on newer data, potentially update features or even the model type, and then redeploy.
So MLOps isn't just deploy and forget. It's a continuous cycle. Monitor, detect, retrain, redeploy.
Precisely. It's about maintaining the model's value and ensuring it remains accurate and reliable over its entire life cycle in production. It's crucial.
Okay, we've seen how powerful Scikit-learn is, especially with pipelines and its ecosystem integration. But it's not the only tool out there. Where does it really shine, and where might you reach for something else?
Scikit-learn is absolutely the king of general purpose, what we call classical machine learning, especially on structured tabular data. Your typical classification, regression, clustering tasks on spreadsheets or database tables. Scikit-learn is usually the first and often the best tool to reach for in Python. Its API consistency is unmatched.
But not for everything. Like for gradient boosting, you mentioned other libraries.
Right. If you need absolutely top-tier performance or need to scale gradient boosting to really large datasets, specialized libraries like XGBoost or LightGBM often outperform Scikit-learn's built-in GBMs. They have more optimizations, native GPU support sometimes. They're focused purely on boosting.
Okay. Now what about if you need deep statistical insights, not just predictions? P-values, confidence intervals, that kind of thing.
Yeah, that's not really Scikit-learn's main focus. Its goal is primarily predictive performance. For rigorous statistical inference, hypothesis testing, understanding the significance of coefficients in a statistical sense, you'd typically turn to a library like stats models. It's designed for that kind of analysis.
Different goals. And then the big one, deep learning. Images, text, audio.
Completely different world. Scikit-learn doesn't really play there. For deep learning, building neural networks for unstructured data, you're using dedicated frameworks like TensorFlow or PyTorch. They're built from the ground up for automatic differentiation, GPU acceleration, and handling the complexities of deep neural networks.
So different tools for different jobs. But here's something fascinating you touched on earlier. Scikit-learn acts like a kind of glue or an orchestration layer even when using other tools.
This is one of the most powerful aspects of the ecosystem. Many of these specialized libraries, like XGBoost and LightGBM, provide Scikit-learn compatible wrappers.
Meaning their models can pretend to be Scikit-learn estimators.
Exactly. They implement the fit and predict methods, get params, etc., following the Scikit-learn API contract.
So you could put an XGBoost model inside a Scikit-learn pipeline alongside Scikit-learn transformers.
Yes. And you can tune XGBoost's hyperparameters using Scikit-learn's grid search CV or randomized search CV right alongside the hyperparameters for your Scikit-learn preprocessing steps.
Whoa, that's huge.
Huh?
It means you could use Scikit-learn's workflow tools, the pipelines, the cross-validation, the hyperparameter search, as a unified framework to fairly compare completely different types of models.
Precisely. You can set up one pipeline structure and easily swap in a Scikit-learn logistic regression, then an SVM, then an XGBoost classifier, and use the exact same validation setup and tuning mechanism to see which performs best, apples to apples. It's incredibly powerful for experimentation and building robust model selection processes.
So Scikit-learn isn't just for its own algorithms. It becomes the essential backbone, the lingua franca that holds the whole classical ML workflow together, even integrating these other high-performance parts.
It really does. From raw data handling with ColumnTransformer, through sequential processing and pipeline to tuning and validation, it provides that consistent structure for the entire journey, culminating in a single deployable artifact.
Wow. Okay, what a journey. We've really gone deep today.
We covered a lot of ground.
Yeah, starting with that core philosophy, that elegant contract behind Scikit-learn's design, understanding the estimator, predictor, transformer interfaces.
Right, and how that consistency enables tools like Pipeline and ColumnTransformer to tame complexity and prevent common errors like data leakage.
Then we looked at extending it, crafting your own custom transformers for domain-specific logic and how they slot right into those pipelines for tuning.
And dug into some key algorithms, understanding GBMs as sequential error correctors, the margin maximization of SVMs, the nuances of ridge, lasso, and elastic net regularization, knowing how to tune them intelligently.
And critically, we bridge the gap from the notebook to the real world, the MLOps journey. Proper model persistence, avoiding the versioning crisis, building serving APIs, containerizing with Docker.
And the absolute necessity of monitoring for data and concept drift in production, keeping those models alive and valuable.
Finally, seeing how Scikit-learn fits in the bigger picture, its strengths and its amazing role as that orchestration layer.
So here's something to think about. Now that you don't just know how to type model.fit, but you understand why Scikit-learn is built this way, its philosophy, its strengths in composability and consistency, and how it glues the ecosystem together. How will unlocking this master key change how you tackle your next machine learning project? Will you think more deliberately about pipelines from the start? Will you be more confident building custom components? Will you push beyond just getting a good score in a notebook and focus on building something truly robust, reproducible, and ready for the challenges of production? How will this shift your approach from just building models to engineering reliable ML systems?